This is a video on factoring quadratic expressions. We'll start with a quadratic binomial. It's quadratic because the highest exponent on a variable is 2. It's a binomial because you have two unlike terms. For this one, we simply use the greatest common factor. So think about what is the largest thing that goes into both 7k squared and 9k. It's k. So we factor that out or pull that out of the two terms. You can think of it as dividing both terms by k, the greatest common factor. So when we do that, we get 7k plus 9. And that's it. That is considered to be fully factored. Number 14 has a greatest common factor other than 1. It's 2. So we're going to do that step first. When we factor the 2 out, we are left with p squared plus p minus 2. We have to check to see if the quadratic trinomial in the parentheses is factorable, because this may not be fully factored if it is. So ask yourself, are there two numbers that multiply to be -2 and add up to +1? In other words, the product is -2 and the sum is 1. Well, this is pretty easy. There aren't too many factors of -2. One of them has to be positive and one of them has to be negative because they have to multiply to become a negative. And the larger one is going to be positive because the sum is positive. So 2 and -1. Now we can write the fully factored form. It's 2 times p plus 2, the 2 I'm obtaining from this number, times p minus 1, the minus 1 obtained from this number. Now it is fully factored. Number 15. We do not have a greatest common factor other than 1 here. So our next step is to see if we can factor this quadratic trinomial. The product number is now going to be obtained from taking the product of the leading coefficient, 2, and the constant term, 21. So it's not simply just looking at the constant term. So 2 times 21 is 42. The sum number, still the middle coefficient, or the coefficient of the linear term, 17. Now we have to find two factors of 42 that add up to 17. If you don't know, start listing the factors. For example, 1 and 42. Well, that's not going to add up to 17. 2 and 21. Not going to work. 3 and 14. That works. So those are our two numbers. Now there's two options. You can use the factoring by grouping method, which is taught in many textbooks, or you can factor using what we at Tenafly call the Nob's method. I'll show you both techniques. Firstly, the factoring by grouping method. So what you do in this method is you start with the leading term from the original expression, 2b squared. Then you write two middle terms that are linear terms, and the coefficients of those two linear terms will come from the magic numbers, so to speak, that we found here. So plus 3b plus 14b. And the last term remains the same as the original. I'm not going to get into why this works. If you have a question about why it works, you can ask me. I'll just demonstrate the technique. Now we are going to find the GCF of the first two terms. It is b. We will factor that out of the first two terms, and we're left with 2b plus 3. This is what's called factoring by grouping, which is used when you have 4 or more terms. Next, we find the GCF of the last two terms. It is 7, and we factor that out, and we're left with 2b plus 3, and we divide both of those terms by 7. Notice that you have a common factor, 2b plus 3. That's what's supposed to happen if this is a factorable expression to begin with. So when you factor the 2b plus 3 out, you're left with b from this first term, and you're left with 7 from this second term. You could also choose to write the b plus 7 first and the 2b plus 3 last. That's it. And you can check your work by foiling or multiplying these two binomials, and you should end up with this, because factoring is undoing multiplication. In number 16, you might say, I'm not sure what to do here. This is not a quadratic expression. Well, watch what happens. Remember, we always try to do GCF first. And actually, I just thought, before I show you that, let me show you the Nobes method for the previous problem. For this one, what you do is you take the first term, 2b squared, and you write it without the squared term, or the square, the exponent of 2. Write it twice as the numerator or numerators of two fractions. Then you take the two numbers that you found that multiply to be the product number. You write those underneath the fractions, in other words, make them the denominators. And then you see if you can reduce the fractions. 2/3 does not reduce, so that remains as 2/3. 2/14 does reduce. It reduces to 1/7, or b over 7. Now you can go right to the two parentheses, two sets of parentheses, and you get the information for those from the reduced fractions. That's it. So either factoring method is fine. Back to number 16. As I was saying, not a quadratic expression, but we can use quadratic techniques once we factor out the GCF. So the greatest common factor here is going to be 4n squared. It's the largest number that goes into all three terms. If you're having difficulty figuring out the numerical portion of it, you can start listing the factors of each and find the largest factor. There's also a method that involves creating a factor tree and looking for common prime factors, but I won't get into that in this video. So when we extract or factor out 4n squared, we are left with 7n squared plus 4n minus 20. Now we have a quadratic expression, and we will try to factor that. The product, 7 times negative 20, is negative 140. The sum is positive 4. Might take you some time to find the factors that multiply to be this and add up to be this. But when you do so, you find that it's going to be involving 10 and 14. You just have to figure out the sign. One is positive, one is negative. Remember, if the sum is positive and the product is negative, then the larger of the factors must be positive. So it's got to be positive 14 and negative 10. Now you can use factoring by grouping or Nobes method. I just prefer Nobes. There's nothing wrong with the other method. I'll still have that there. Let me create my two Nobes fractions, 7n and 7n. Fraction bars, and then the numbers that I found from here go underneath, and then I reduce. So this becomes n over 2, and this becomes nothing. Same thing. 7/10 does not reduce. Now I know what to write in the fraction, or in the parentheses, excuse me. What I write comes from these reduced fractions. 7n minus 10. And that is the fully factored form The reason for knowing how to factor, well, there are several reasons. One is they help you to simplify expressions, because you can find common factors that can be removed, in other words, canceled. And also, they can be helpful in solving equations, because if you can factor one side of the equation and have the other side set equal to 0, you can take advantage of what's called the zero product property in order to solve the equation.